Hello everyone. So today's lesson is going to be regarding chapter 1, which is all about structure and bonding. Here's a schematic diagram of the atomic structure of an atom, and we know that atoms are the simplest basic building blocks of matter, and that they are composed of three different subatomic particles. We have the positively charged protons, the neutrally charged neutrons, and the negatively charged electrons. The protons and the neutrons make up the nucleus, and the nucleus is located at the center of the atom. The electrons, on the other hand, are in the electron cloud, or basically in the orbits that surround the nucleus. In the early 1900s, a lot of the scientists tried to propose what the structure of an atom looks like, and one of them was this guy named J.J. Thomson from Cambridge University. He's actually the guy that discovered the electrons, who later received the Nobel Prize. After the discovery of the electrons, he proposed his own model of the atom. He called it the plum pudding model. As it turns out, that model was incorrect, and it was proven by this guy named Ernest Rutherford, who later came up with his own model of the atom, and he called it the nuclear theory. So it's basically the atom consisting of the nucleus, and the nucleus contains most of the atom's mass. And this is due to the positively charged protons. And at that time, the neutrons were not discovered yet. It was 10 years later when James Chadwick discovered these neutrally charged subatomic particles. And then we also have Bohr's model of the atom, but this model only works for the hydrogen atom. The best model for the atomic structure is the quantum mechanical model, which basically suggests that electrons reside in the orbitals. And the orbitals can be described by four quantum numbers. You have the principal or main quantum number, you have the angular momentum quantum number, magnetic quantum number, and spin quantum number. When you look at the periodic table of the elements, you'll notice three main things: the symbol of the element, the atomic number, and the atomic weight. The atomic number indicates the number of protons and also the number of electrons. Titanium, for instance, has atomic number 22, which means that a single atom of this element contains 22 protons and 22 electrons. The atomic weight is also known as the atomic mass. This is defined as the weighted average of the mass of all its isotopes, and it has the unit known as atomic mass unit, or AMU for short. The term mass number is specifically for isotopes, and it indicates the number of protons plus neutrons. Carbon-12 and carbon-13 are the two most abundant isotopes of carbon. Carbon-12 has 6 protons and 6 neutrons, whereas carbon-13 has 6 protons and 7 neutrons. So there are two types of atoms, ions and isotopes. Ions are charged atoms, meaning they carry either a positive charge or a negative charge. Cations are positively charged, whereas anions are negatively charged. Isotopes, on the other hand, are atoms of the same exact element, but with different number of neutrons, which also means they have different mass numbers like carbon-12 and carbon-13. Another example is hydrogen. Hydrogen has 3 isotopes, as shown down here: hydrogen-1, deuterium, and tritium. In order to calculate the number of neutrons, all you have to do is subtract the two numbers. So for example, the first isotope here is hydrogen. When you subtract the two numbers, 1 minus 1, you get 0. So this isotope of hydrogen, which is also the most abundant, has 0 neutron. The second one here is deuterium. When you subtract the two numbers, you get 1 neutron. And finally, tritium has 2 neutrons. Notice the notation, how the isotopes are written. You have the mass number up top and the atomic number at the bottom. So you can see that the mass number is usually larger than the atomic number. The mass number is written up top and the atomic number right below it, which is different from what you'd see in a periodic table. The reason is because the atomic mass in the periodic table is the weighted average mass of all the isotopes of that given element. In the periodic table, The elements are arranged in order of increasing number of protons, or in this case, atomic number. They are also arranged in rows and columns, also known as groups. Elements in the same row have about the same atomic radius, and elements in the same column have very similar electronic and chemical properties. So for example, when you look at group 1A elements, these are the alkali metals, they all have very similar properties. These are the most reactive metals in the periodic table. Similarly, group 7A elements, the halogens, are the most reactive non-metals. And finally, group 8A elements, the noble gases, these are the most stable elements in the periodic table, which also means that they rarely react with other elements. In general chemistry, you learn about the quantum mechanical model of the atom. And in this model of the atom, there are different energy levels. The energy level increases as you move farther away from the nucleus. These energy levels are described by the principal or main quantum number. You can have n equals 1, which is the first energy level, n equals 2 for the second energy level, and so on and so forth. The higher the n value, the greater the energy. And within these energy levels, you have the energy sublevels, which are described by the angular momentum quantum number. These are your S, P, D, and F sublevels. And in these sublevels, there are orbitals, which are described by the magnetic quantum number. These are the S, P, D, and F orbitals. There's an S orbital in the S sublevel, 3 different P orbitals in the P sublevel, 5 D orbitals in the D sublevel, and 7 F orbitals in the F sublevel. And finally, the electrons reside in these orbitals with quantized values of positive half and negative half, which means they either spin up or spin down. In the quantum mechanical model of the atom, atomic orbitals are defined as the regions of space within an atom where there's a high probability of finding an electron. And there are 4 main types, the S, P, D, and F orbitals. But here in organic chemistry, we only care about the first 2, the S and P orbitals. The S orbital is spherical in shape and has the lowest energy of all the orbitals. The P orbital has a dumbbell shape, as shown here, and it contains a node at the nucleus, which means that electrons cannot exist here. In the periodic table, the first row contains the first energy level, or n equals 1. This means that there can only be a maximum of 2 electrons that can exist here. Hydrogen has 1 electron, which resides in the 1s orbital. Helium, on the other hand, has 2 electrons, both of which reside in the 1s orbital. The second row in the periodic table contains the second energy level, or n equals 2. The elements in this row can access a total of 4 orbitals, 1 from the 2s and 3 from the 2p. The 2s sublevel contains only 1 orbital, which is the s orbital. The 2p sublevel, on the other hand, contains 3 different orbitals, the 2px, 2py, and 2pz orbitals. And combining them all together, and you have the 2p sublevel. All of the second row orbitals, as well as the D and F orbitals, can hold a maximum of 2 electrons. The first and second row elements can hold a maximum of 8 valence electrons, coming from the outermost S and P subshells. 2 electrons in the S subshell and 6 electrons in the P subshell, for a total of 8. Valence electrons, by definition, are the electrons in the outermost S and P subshells that are involved in bonding and chemical reactions. An element's number of valence electrons matches the element's group number. For example, group 1A elements contain 1 valence electron. Group 2 elements have 2 valence electrons, and group 8A elements contain 8 valence electrons. Alright, so let's look at this one problem here. While the most common isotope of nitrogen has a mass number of 14, a radioactive isotope of nitrogen has a mass number of 13. Nitrogen-13 is used in PET scans by physicians to monitor brain activity and diagnose dementia. For each isotope, give the following information. A, the number of protons, B, the number of neutrons, and C, the number of electrons in the neutral atom, and D, the group number, and E, the number of valence electrons. All right, so let's look at A, B, and C first. Number of protons, electrons, and neutrons for each isotope. So we have nitrogen 13 and 14 here. All right, so we have nitrogen 13 and nitrogen 14. All right, so these two right here are basically a second notation, a second way to write isotopes. The more common one is this. So you have nitrogen 13 and nitrogen 14. And then you look at the periodic table and see what the atomic number is for nitrogen. So the atomic number for nitrogen is 7. So we're going to put 7 right here. Right, so this is the most common notation where you have the mass number right here up top, and then the smaller number, which is the atomic number, at the bottom. And so what you're going to do is you're going to subtract the two numbers, and what you have is the number of protons. All right, so 13 minus 7, that gives us 6 protons. And, I'm sorry, 7 protons. 7 protons. And then you subtract it to 13 minus 7, you get 6 neutrons. All right. And because this is an isotope and it's not an ion, it's a neutral atom. It's a neutral isotope. And so the number of electrons would match the number of protons. So in this case, we have 7 electrons as well. All right. And for nitrogen 14, same thing. So it has 7 protons. And then subtract the two numbers, 14 minus 7, 7 neutrons. And again, this is also a neutral isotope. So 7 electrons as well. All right, so that basically answers A, B, and C. And now for D, the group number. So the group number is 5 for nitrogen in the periodic table. So this is group 5A. And so for E, the number of valence electrons basically matches the group number. So 5 valence electrons. Atoms combine to form molecules through chemical bonding. Chemical bonding can involve either the sharing of electrons or the transfer of electrons from one atom to another. And this brings us to the two types of chemical bonds. There's ionic bond and covalent bond. Ionic bond is the bond utilized in ionic compounds, and the electrons are transferred from the metal to the nonmetal. Covalent bonds, on the other hand, are utilized in molecular compounds, also known as molecules, by sharing the valence electrons between nonmetal atoms. So let's take a look at ionic bonding first. As I've mentioned earlier, ionic bond forms in ionic compounds. Metals tend to lose electrons, whereas nonmetals tend to gain electrons. When metals lose an electron, it renders them a positive charge, and they are called cations. In contrast, when nonmetals gain an electron, it renders them a negative charge, and they are called anions. And this makes ionic bonding an electrostatic type of interactions between positive and negative charges. Sodium, for example, has a positive charge, which makes it a cation. And this chlorine right here has a negative charge, which makes it an anion. So we have a sodium ion and a chloride ion, which make up sodium chloride, an ionic compound. The second type of chemical bond is covalent bond. And in covalent bonding, electrons are shared between non-metal atoms, like carbon, nitrogen, and oxygen. These bonding electrons can also be shared by two atoms of the same type, such as in homonuclear diatomic molecules like oxygen gas, nitrogen gas, and fluorine gas. Compounds that use covalent bonding are also known as molecules, like water, alcohols, and sugars. Here's problem 1.2. Label each bond in the following compounds as either ionic or covalent. So what this problem is basically asking is, what type of compound do we have? If you have an ionic compound, that uses ionic bonds. If you have a molecule or molecular compound, then it uses covalent bonding. And so an ionic compound contains a metal and a nonmetal in its chemical formula. A molecule or a covalent compound contains only nonmetals. So all you have to do is analyze the chemical formula and see whether you have a metal or a nonmetal or a combination, right? So for fluorine gas, F2, you can see that fluorine is a nonmetal and there's no metal anywhere in the chemical formula. And so it makes this compound a molecule. So this is a molecule. And because it's a molecule, it uses covalent bonding. All right, the next one here is lithium bromide. So we know that lithium is a metal and bromine a nonmetal. And so what we have here is an ionic compound that uses ionic bond. The third one here is ethane, which consists of a bunch of nonmetals. And so this is a molecule, and so therefore it uses covalent bonding. For the fourth example here, we have sodium NaNH2. Okay, we have sodium amide here. So this is a metal plus a bunch of nonmetals, right? So it's an ionic compound which utilizes ionic bond. And the last one here is sodium NaOCH3. And so we have a metal and again a bunch of nonmetals, which is an ionic compound, and this utilizes ionic bonding. So earlier I mentioned that valence electrons are the electrons involved in the formation of bonds or involved in chemical reactions. And the number of valence electrons basically matches the element's group number. So for example, group 1 elements contain 1 valence electron, group 2 elements contain 2 valence electrons, and so on and so forth. Now, atoms containing 1, 2, 3, or 4 valence electrons can only form 1, 2, 3, or 4 bonds respectively in neutral molecules. So meaning elements in group 1 can only form 1 bond. Elements in group 2 containing 2 valence electrons can only form 2 bonds, and so on and so forth. Hydrogen, 1 valence electron. Boron has 3 valence electrons, so it can form 3 bonds. Now, atoms with 5 or more valence electrons can form enough bonds to complete its octet. So nitrogen with 5 valence electrons can form 3 bonds, right? 5 plus 3 equals 8, which is the octet rule, basically. Whereas oxygen with 6 valence electrons can form 2 bonds. 6 plus 2 equals 8. And sulfur, phosphorus, same thing. Phosphorus can form 3 bonds, sulfur can form 2 bonds, and so on and so forth. So here's a few more examples. We have hydrogen, carbon, nitrogen, oxygen, and one of the halogens. So we have either fluorine, chlorine, bromine, or iodine. So we know that hydrogen is in group 1, so it has 1 valence electron, and so that means it can only form 1 bond. Carbon is in group 4, and so it has 4 valence electrons, so that means it can form a total of 4 bonds. And any elements containing more than 5 valence electrons, you subtract their number of valence electrons from 8, right? So 8 minus 5 for nitrogen. Nitrogen can form 3 bonds. Oxygen is in group 6, so it has 6 valence electrons. Subtract that from 8 and you get 2. So it can form 2 bonds. And finally, group 7 elements, the halogens, subtract that from 8 and you get 1. So these halogens can only form 1 bond. In terms of the non-bonding electrons, these are the unshared electrons, and they are not involved in bonding. And these are also known as lone pairs. How do we determine the number of lone pairs for a specific element. So for hydrogen, that would be zero bonding, non-bonding electrons. As you can see, there are no lone pairs around hydrogen. Same thing for carbon, there are no lone pairs. But for nitrogen, you have one lone pair here. And then for oxygen, you have two lone pairs. And for halogens, a total of 3 lone pairs. Here's problem 1.3. How many covalent bonds are predicted for each atom? So this will depend on the number of valence electrons. So let's take a look at the number of valence electrons for these elements first. So oxygen is in group 6, so it's got 6 valence electrons. Aluminum is in group 3, so it has 3 valence electrons. Bromine is a halogen, so it has 7 valence electrons. And silicon is right below carbon, and so it has 4 valence electrons. So again, it's asking how many covalent bonds are predicted for each atom. So for oxygen, it has greater than 5 or greater number of valence electrons, and so you subtract its number of valence electrons from 8. So 8 minus 6 is 2, so it can form 2 bonds. Aluminum has less than 5 valence electrons, and so it can only form 3 bonds. And here we have bromine, which has 7 valence electrons. Subtract this from 8 and you have 1 bond. And finally, silicon is basically similar to carbon. It has 4 valence electrons, and so we can form 4 bonds.